our notes around from yesterday? Let me just see them real quick. I know where we stopped, but there's a couple of corrections I'd like to make. Oh, you didn't? I want good. Oh, baby. Okay, where? Ah, yes, here we go. I wanted to make 2 corrections. So we'll just start with 2 corrections. Okay, 1. This is a minor correction, but anybody from Trinidad and Tobago who is watching, I only mention this because Google finally fixed their, I don't know, the system they have that'll tell you how many times you've had your videos watched. And I found out they also tell you now what country those people were in. And it turns out that on lecture 4, if you rank how many times it's been watched per country, the United States is only number 4 on that list. Number 1 is Trinidad and Tobago. Number 2 is Yemen. And number 3 is South Korea.
I'm from Trinidad and Tobago.
You're from Trinidad and Tobago?
Yeah.
Either this is amazing or you're pulling off one of the great jokes right now. Really?
Yeah, I'm from Trinidad, but not from Tobago. But
oh, I knew it!
No, the whole country name is Trinidad and Tobago, but I'm just from Trinidad.
I would never have guessed.
I know.
I would never have guessed. My best friend growing up was from Trinidad and Tobago. Rudy Armstrong. Rudy Armstrong, if you're out there, give me a call. Okay. All right, what's wrong with this problem as I wrote it? Okay, we sat through and we said, okay, we need to use L'Hopital's rule and da-da-da-da-da. We did some fun stuff. We got an answer. But as I wrote this isn't even a well-formed problem.
Can't we just plug in 1?
Can't we just plug in 1? Well, that would mean this is a continuous function, which in particular would mean 1 is in the domain, which would mean you can just plug in 1, but 1 here is going to give you a 0 in the denominator. So no, we definitely couldn't do that. Okay? Why is there a problem? Okay, I mean, the limit, you don't actually plug in 1. Chris?
Because the limit can't exist from the left?
Exactly, right? If I put in numbers, if I come in from the left side, right, from numbers smaller than 1, the 4th power of that number will still be smaller than 1. When I subtract 1, I then get a negative number, and then I take a square root. Okay? So how do I fix this problem? Well, I just consider the one-sided limit. Okay? And then everything we did works just fine. Okay? So that was correction 1. Correction 2 is more serious. When I stated L'Hopital's rule, I wrote this down. This is fine. There's nothing wrong with this. Right? It works exactly the way I said. The only thing which is off is I completely biffed up the hypotheses. Okay? I wrote down as my hypotheses that f of a equals 0, or this could be infinity or minus infinity, right, equals g of a. And I wrote that g prime of a should not equal 0. I completely flubbed this. Okay, what it should say is that the limit as x approaches a of f of x should be 0. Right? And the same thing on the other side with g of x. Okay? Or infinity, right? Or minus infinity. And over here, this is actually just completely nothing. It should be that g prime of x is not 0 around a, but g prime of a can be 0. We allow for that possibility. Actually, g prime of a could be 0, but in a neighborhood around a. Okay, nowhere near it is it 0. Okay, but at a it could be 0, but around it not. Okay, so these are the actual hypotheses that you want. And correction 3 is not a mistake on my part, but I did look up the story, and L'Hopital bought the rule from Bernoulli. So I believe that's what I had originally said before Tom gave us is a high school teacher's version. But at least according to Stewart, L'Hopital bought the rule from Bernoulli. Incidentally, there is a new homework assignment, okay? And I put on that homework assignment the very first problem that the world saw, other than these two guys, that the world saw that used L'Hopital's rule. Okay, so L'Hopital wrote the very first calculus textbook, right? So, and he put this rule, which he bought from Bernoulli, into the textbook. And to demonstrate its usefulness, he wrote down this very disgusting problem, which is now on your homework. Yeah.
Is that Friday?
Yeah, that will be due the following Friday, of course. Okay. All right, so those are the corrections. So today, so you already noticed when I use L'Hopital's rule, every time I used it, right, when I have an equal sign, I put a little L hyphen, not hyphen, the heck is that called? Quotation mark? Apostrophe, we'll go L apostrophe H under it, right, because it lets people know what's going on. And typically I'm just going to shorten it to this, because I think you guys can figure out what I mean. So this is L'Hopital's rule continued. Okay. And we're going to talk about some of the other indeterminate forms that we didn't get to. So for instance, 0 times infinity. Okay. What was the problem? Now, remember, our convention, this does not actually mean multiply the number 0 times the number infinity. Okay? This is, you have a function whose limit at a point is 0, and another function whose limit at a point is infinity. And you're asking what happens when you multiply those functions together and take the same limit. Okay? So, as some function gets close to 0 and another function gets close to infinity, and you multiply them, what happens to the product? Okay? And we decided, well, if it goes to 0 faster, then the product might go to 0. If it goes to infinity faster, it might go to infinity, or it might balance out. For instance, right, let's say I have some function, and it's going to 0, and when it gets to point 1, this is at 1. Okay? Their product is now 0.1. Okay, now let's say in the time that it takes this function to get down to 0.01, this one goes up to 1,000, okay, or 10 to the third. Okay, now what is their product going to be? Yeah, 10, right? This is 10 to the negative 2. Okay, and let's say when it gets down to 10 to the negative 3, this one goes up to 10 to the 7th. What's their product going to be? 10 to the 4th.
Wow.
Okay? And if the next time, when this gets to 10 to the negative 4th, this is up to 10 to the 20th, right? Now it's 10 to the 16th. Okay, now, to you, if you had to guess, what will the limit of this function be? Or the product of these functions? It's going to infinity, right? This thing, the product just keeps growing. Okay? But what if instead, okay, at point 1, it was at 1, but it's, okay, this is 10 to the negative. 10 to the negative 1. At 10 to the negative 2, it was at 5. And at 10 to the negative 3, it was at 5.1. Right? And at 10 to the negative 4, it was at 5.01. And at 10 to the negative 5, it was at 5.001. Right? What do you think this is going to approach? What's happening to the products here? Yeah, it's getting small, right? This is just, I mean, this is getting close to 5, clearly. Okay? Oh, actually, I'm making these go the wrong way. I can't make 0 and 1, because it's got to go to infinity, so I'll put 1s in here. Okay, so it's getting marginally bigger. Okay? Okay, but I keep multiplying it by a number which is getting closer and closer to 0, and it's getting closer and closer to 0 faster. Okay, maybe when it goes down here to, just to get to 5.1111, it all goes to 10 to the negative 7. So this product might go to 0. Okay? But there's another way it could work. Let's say it started at 0.1, and this is at 1. right, or 10 to the negative 1. And then at 10 to the negative 2, this went to 10. And 10 to the negative 3, this went to 10 squared. And 10 to the negative 4, this went to 10 cubed. Now what's going on? We get 10 to the negative 1, 10 to the negative 1, 10 to the negative 1, 10 to the negative 1. So here this is going to 0 and this is going to infinity, but the product is actually just 1 over 10. Right? 10 to the negative 1. Okay? So that's why we call this an indeterminate form. You can't determine without more information, right, what this limit will be. Okay, another indeterminate form we're going to look at is 0 to the 0. Right? Of course, we know if 0 to the something is 0 to the 5th power. 0. Right? What about 0 to the 10th power? 0, right? 0 to some power is always 0. On the other hand, if I take 5 to the 0th power, get 1. If I take 10 to the 0th power, 1. So what should 0 to the 0th power be? Well, let's see. 0 to something is 0, but something to 0 is 1. So which one should it be?
0.5.
0.5. That's a clever answer. Okay. So again, this is going to be an indeterminate form. Without knowing, right? I mean, again, this is where I have some function which is going to 0 and another function which is going to 0, and I take the limit. Without knowing more, I can't answer that question. It's just an indeterminate form. Okay? And we're going to look at some other ones. Things like 1 to the infinity. Okay? Should this be 1 or infinity? What do you think? Well, it's another indeterminate form. Okay? Infinity minus infinity. You have something growing really fast, but you subtract something that's growing really fast. Well, it depends. Which is growing faster? Okay? Without knowing which one is growing faster, you can't decide what this is. Okay? So there's all sorts of fun stuff like this we're going to look at. All right. Now, at the end of yesterday, I wrote out the limit. The limit as x goes to 0 from the positive side of x ln of x. What indeterminacy type is this? Right, so these are indeterminacy types. The first one, right? This is x goes to 0, and ln of x goes to negative infinity, okay? So I don't make a distinguishment between negative infinity and positive infinity in terms of types, because what's a negative amongst friends, right? It's no big deal. Okay, so this is 0 times infinity indeterminacy type. Okay, and what I claim is that we can fiddle with this thing so we can actually use L'Hopital's rule. So how might we do that? Well, L'Hopital's rule is set up, you need a function divided by another function. Okay? So how could we get a quotient? Well, we're going to use the fact that you can always turn something into a quotient by giving it a negative exponent. Right? Remember, if you have B. If I have something on top and I want to move it to the bottom, I just move it to the bottom, but I have to give it a negative exponent. Okay? And if I want to move something to the top, I just give it a negative exponent. Yeah? Okay. Giving a negative exponent just switches you from top to bottom or bottom to top. Okay, see, that's how you can move things up and down. So, well, I have two functions here. I have a choice which one I could move. Alice says you move the first. Okay, let's try it. So I write ln of x, and if I put x on the bottom, I have to give it a negative exponent. Okay? Negative exponent moves you up, moves you down. And if you have a negative exponent, right, remember that meant you could move it back up and you just get rid of it. Okay, so it's the same thing. If you take away a negative exponent, you move it up, move it down. Okay, now, what kind of indeterminacy type is this function? Right? Well, it's one that we looked at yesterday. We didn't rewrite here, but okay, the top goes to, well, negative infinity, and the bottom goes to, we have a function here, 1 over x. What happens as x goes to 0? Infinity, right? 1 over x, right? Remember, goes, right? As x goes to 0, the bottom of the fraction goes to 0. This bit goes to infinity, right? So you're actually at negative infinity over infinity, right? So we just call that infinity over infinity type. Okay. Now, whenever you have a 0 times infinity type, if you just make this 1 over that bit, right, or move it down and give it a negative exponent, it's automatically going to become an infinity, right? Because you have a 0, so if you make it 1 over a 0, it's going to become an infinity. So you can always turn a 0 times infinity type into an infinity over infinity type. And once you're in this type, what rule can we use? L'Hopital's rule. Okay, so L'Hopital's rule says you keep the limit the same, but you take the derivative of the top and the bottom. Okay, the derivative of ln of x.
1 over x.
1 over x, or if you like, x inverse. Okay. And what's the derivative of x to the negative 1? Very good. Negative x to the negative 2. Ah, this is very nice. Now I get rid of that ln of x. Right? Now everything's powers of x's. I know how to play with those. Well, let's see. Maybe I should get all the x's together. If only I can move this x up. Oh, that's easy enough. You want to move something up or down? You just either add or get rid of a negative exponent, right? So here I have a negative exponent. Move it up, I'll get rid of it. So I get x squared, and I'll take this minus and just move it to the front, or even outside. Okay, I get x squared times x inverse. What's x squared times x inverse? X. Okay, so I get negative limit x goes to 0 from the positive of x. Okay, x goes to 0, this goes to 0, negative 0, 0. There's our limit. All right. What does this tell us? So let's go back to the beginning. Okay, we had 0 times infinity type. Right? And it ended up getting pulled to 0, which means that the x must be going to 0 faster than ln of x is going to minus infinity. Yeah? Okay, so it tells you something about how fast these things are moving. Okay. Any questions about that? So the general rule is you see a limit problem and you say, oh, okay, it's something nasty. That's going to 0, that's going to infinity. And you think, oh, wait a second, that's 0 times infinity type. I can use L'Hopital's rule. I just have to turn it into infinity over infinity type. Now, here's a question. What if I had not listened to Adam? And instead of putting the x on the bottom, I put the ln of x on the bottom? Let's see. Let's see what happens. Well, first, what kind of type am I going to get? I started 0 times infinity, and now I move the infinity to the bottom. Right? Which means I'm doing 1 over infinity on the bottom, which means it's going to 0, right? So I'm getting 0 over 0 type, okay, which is another one we looked at yesterday. Okay, so it's again somewhere where I can use L'Hopital's rule. I'll write this as x over ln of x to the minus 1. Okay? I have to put a minus 1 up there, give it a negative exponent if I want to move it down. And now if I use L'Hopital's rule, because I'm in the 0 over 0 type, okay, derivative of x is 1. Okay, what about this? Okay, I do negative ln of x to the negative 2 times the derivative of ln of x, which is x to the minus 1. And if I rewrite this, okay, I can put the x back up top, right? And, well, for that matter, I can put the ln of x up top, but let's just leave it down there for a second. I'll pull this minus out since we don't need to worry about it. I get ln of x to the minus 2, right? Or, I mean, this bit is x ln of x squared. Either way. We seem to have made the problem worse. Right? We've squared this ln of x, but that doesn't help us any. We already knew it was going, right? Over here it's going to minus infinity. Okay, when you square it, it's going to positive infinity. Whoop-de-doo. We still have a problem, okay? So what this says is sometimes, I mean, you have to make a choice, and you could choose wrong. Now, you might think, we know, I mean, polynomials are somehow nicer than logarithmic functions. So maybe that's the one you should always put to the bottom, okay? Okay, so let's do a related example and see if that's true. Okay, now, natural log of x has an inverse function. What's the inverse of natural log of x? E to the x. I'm so happy. So let's look at the limit as x goes, let's say first infinity of x times e to the x. Okay. Quickly, what's the answer?
Infinity.
X goes to infinity. E to the x goes to infinity. Infinity times infinity. There's no problem. You have two things which are both getting really, really big. You multiply them together, they're getting really, really big. There's no ambiguity here. It's infinity. Okay. What, however, would we do if I was going towards negative infinity? Because now, okay, x is going to negative infinity. Where's e to the x going? To 0. Okay, so I'm in one of these nasty types, right? I see negative infinity, right? And we drop the negative times 0, or 0 times infinity, if you like. That's my type. Okay? Now, we just said that if you're in the 0 times infinity type, you can take one of these, add a negative exponent to move it to the bottom of a fraction. And then you'll either be in the 0 over 0 or the infinity over infinity type, depending on which one you choose. Okay? So let's take our conjecture that you should always move the x down to the bottom. So we can rewrite this as the limit as x goes to minus infinity of e to the x over x inverse. Right? To move it down, we give it a negative exponent. Okay, so now we know we're in the the 0 over 0 type. Because we took the thing which was going to infinity and moved it down. So we get rid of the infinity, we make it a 0. So we're in the 0 over 0 type. We can use L'Hopital's rule. So this is limit as x goes to minus infinity. Okay, derivative of the x. E to the x, no problem. And the derivative of x inverse.
Negative 1 x to negative
Negative x to the negative 2. Ooh. We've somehow, let's put this back in multiplicative in the multiplicative way, right? This is now, put the negative out front, x squared e to the x. We've put ourselves in exactly the same problem as we had before, only now it's a square. Right? Which is exactly the problem we had here. Right? So here, moving the x term down doesn't help. Okay, let's see what happens if we move the other term down. Right, the e to the x part. We have this, and we're going to rewrite it. Only now I'm going to move the e to the x down, so that picks up a negative exponent. Move it down and get a negative. Okay? Now, we started with a, well, it was infinity times 0 type, and it's going to become an infinity over infinity type. Okay? So we're in the infinity over infinity type, right? Where I'm leaving off pluses and minuses. Okay, so I use L'Hopital's rule. And I get the limit. As x goes to minus infinity, okay, derivative of x is... God, you guys are just dead. Okay, what's the derivative of e to the minus x? Negative e to the negative x. Right, it's e to the negative x times the derivative of negative x, which is negative 1, so you get negative e to the negative x. Okay, now let's see what happens. As x goes to minus infinity, negative x goes to
Infinity.
positive infinity, and so e to the negative x goes to infinity. And so, forget about this minus, 1 over e to the minus x goes to 0, right? The bottom is, forgetting about the negative, the bottom is really, really big, so the fraction must be getting really, really small. It must be going to 0, so this negative, of course, in the end doesn't matter. So this goes to 0. So what does that tell us? Well, go back to our original infinity times 0 type, right? Or negative infinity, whichever you like. Okay. The 0 is winning. Okay, because that's what the limit was. Which means that e to the x must be going to 0 much faster than x is going to minus infinity. Okay. And this isn't so surprising, because yesterday, right, we saw that polynomial growth is not as strong as exponential growth. Okay. But we did just see that with x ln of x, that polynomial growth is faster than logarithmic growth. Okay. So exponential growth, very, very fast. Polynomial growth, logarithmic growth, very slow. Okay. Any questions? Okay, so this is not so bad. Let's try to do one of the exponential type ones. We'll get to see an old friend come back to help us. All right. Let's do something easier. Let's look at the limit as x goes to 0. And let's just look on the positive side. I don't want to worry about square roots of negative numbers. Let's look at that. That's kind of a strange function, x to the x. And I want to know what the limit is. So this is of type 0 to the 0. Okay? Any ideas? Well, do you remember how we took the derivative of something in the form x to the x? Tom?
Oh, no, I just haven't.
Oh, what idea?
Natural log.
That's a very good idea, right? How did we take the derivative of x to the x? Yeah, we used ln. Remember, we would look at if we had y equals x to the x, took ln of both sides,
Natty log.
and then we said, yeah, but exponentiation is turned into multiplication by natural log. So this was x ln of x. Right? And then you could take the derivative using the chain rule of both sides. And then at the end, you'd have to use e to get everything back into the right form. Okay, but this gives you another way to do it. Okay. Well, if it works once, maybe it'll work again. No? Okay, well, we just saw here, if we set y equal to x to the x, and we take the natural log, then ln of y is equal to x ln of x. Well, let's look at what happens if we take the limit as x goes to 0 of ln of y. Well, certainly, this will be the same as if we take the limit, let's say from the plus side. We take the limit as x goes to 0 of x ln of x. No? So what is the limit as x goes to 0 of x ln of x? We just computed that, right? That was the first example we worked. And we just saw it was 0. Okay, fine. So this is 0.
Why did you put y?
Why did I put a y?
Yeah.
Oh, I came back to this y equals x to the x. Right? It's exactly what we do with derivatives. Right? And took ln of both sides. Okay. And this is a general rule. If you have a variable in the exponent, things are very difficult. So you take the log of both sides, and then all those exponents will come down. Right? And then you don't have to worry about things anymore. Okay, so the limit of the natural log of y is 0. I really want the limit as x goes to 0 of y. So how do I get rid of this natural log? E. E. If this limit is 0, what if I took E and raised it to this limit? Well, then it equals E raised to 0. Right? Because, well, this limit is equal to 0. And of course, e to the 0 is 1. Okay, now, what would be really nice is if I could somehow take this limit and move it to the front. Right? Because then what would happen? I'd have e to the ln. And those are going to cancel. Okay, so let's think now. How could I move a limit inside of a function? When does it make sense to do that? There's a certain condition that we'd be looking for on the function for that to happen. What kind of nice condition do we have on functions and limits? We only have a couple properties of functions that we deal with in this course. 2, really. Continuity and differentiability, right? Now, which of those 2 properties has to do with being able to just plug a number into the limit? Continuity. Okay. Let's quickly put this, make a little room over here. Just a little side note. Our continuity condition says the following. A function is continuous at A if this limit equals what? F of A. Okay. But there's a different way to write F of A. What we really mean for continuity is that you can put this limit inside the function. Oops. And of course, what is the limit of x as x goes to a? A. Yeah, A. As x goes to A, x goes to A. Okay? And of course, we recover what we want. But this intermediate step tells you that a function is continuous at a point if and only if you can swap the limit and the f, right? If you can put the limit on the inside. Okay? Now, is the exponential function continuous? Yes. Which means you can swap the limit and e. This says that you can put it on the outside, right? Instead of reading it this way, read it this way. If the function is continuous, you can take this limit and pull it out. Okay? So here, e to the x is a continuous function. I pull the limit out. Okay? And of course, what is e to the ln? Well, those are inverse functions, right? So e to the ln of y is just
What?
y. And so the limit as x goes to 0 of y is 1. And of course, y was x to the x, which is what we wanted. Right? The limit as x goes to 0 plus x to the x is 1. So this is, I'm not sure if it's surprising that it works this way. But you certainly didn't know, right? I mean, you take a number and raise it to itself. Okay, well, you get some other number, right? Now, make that number really, really small. Well, it's getting really small, so it's getting closer to 0, so you expect things to be getting smaller. But you're raising it to a power which is getting close to 0, so you expect it to be getting close to 1. And who should win out? Well, it turns out the one side wins out. Okay, so to me, this suggests that if you had to pick a value for 0 to the 0th power, 1 should be the right choice, not 0. And sadly, Chris, not. Okay, but you don't have to choose. It's always an indeterminate form, okay? And we can come up with other functions like this where it's still going to 0, but the limit will be 0. Okay? So this can happen. So when you're working problems that have the variables in the exponent, you're going to have to use this trick a lot, where you take the log of both sides, and then at the very end, remember that because e is a continuous function. Right, where's e continuous, by the way? What's the domain of e to the x?
All of it.
It's all reals. Where is it continuous? All reals, right? It's a beautiful function. Differentiable everywhere. Not just continuous everywhere, but differentiable everywhere. So you're always allowed to do this nice swap. Okay. Any questions about this? Try to concoct another example. Okay. How about, I'll let you guys tell me what the problem child should be. What value here will make this problem interesting?
Pi over 2.
Very good. Pi over 2. Okay, why pi over 2?
Secant is 1 over cosine, and cosine is 0 at pi over 2.
Sure. Secant is 1 over cosine. Tangent is sine over cosine, right? So both times you have a cosine in the denominator. And If cosine becomes 0, you have a problem. Okay? So where is cosine 0? Well, the kind of the easiest answer is, well, let's see, it's the x-coordinate when it becomes 0 there, right? Pi over 2. Okay, now, there's not going to be, I mean, okay, so what's happening is it goes to pi over 2, right? Well, you think, it's going to 1 over infinity, right? But there's a little subtle problem if I just leave it like this. Let's draw our unit circle. Okay, remember, cosine is the x-coordinate, okay, on the unit circle. So up here is pi over 2. So if I choose a point over here, then the cosine is some small negative number, a positive number. Yeah? And so 1 over it is going to be some big positive number. But what if I choose it over here? What happens to cosine? It's now negative. So I'd be getting 1 over some small negative number, so I'd be getting some big negative number. Okay? Which means these limits individually won't even exist, right? Because from one side they're coming positive, and from the other side they're coming negative infinity. Right? So I should really choose a side to come in on. Plus, okay, so if I'm doing the plus, that means I'm bigger than pi over 2, so everything's going to be negative. Is that okay? Okay, maybe the other side. Okay, so we'll do this right, so everything's positive. Okay, so now this is going to positive infinity, and this is going to positive infinity. Right? So what type is this? Infinity minus infinity type. Okay. Now sometimes this can be the trickiest type to deal with, but in this case it won't be so bad. We can't apply L'Hopital's rule immediately, right? Because it's not a quotient. But how could I turn this into a quotient? Well, there's some hidden quotients here, aren't there?
Sine over cosine.
You're right. Tangent is sine over cosine. Secant is 1 over cosine. So let me just rewrite this. Right? This is 1 over cosine of x minus sine over cosine of x. Ah, two fraction, common denominator. One minus sine of x over cosine of x. Okay. Now, know that this. I mean, we haven't done anything, right? We've just rearranged the terms. We haven't factored or canceled or any fun stuff. So this should still be in some sort of indeterminacy type. So what do we get? Well, if I put in pi over 2, the sine, I get
1.
All right? It's the y-coordinate, so it's 1 up here. So I get 1 minus 1, which is 0. And cosine, we already know, is going to 0, so I must be getting the 0 over 0 type. I'm in the 0 over 0 type. What rule can I use? L'Hopital's rule. So, I take the derivative of 1 minus sine of x. What's the derivative of 1? 0. Okay, that's gone. Derivative of minus sine is minus cosine. And on the bottom, the derivative of cosine is minus sine. Okay, so, of course, the negatives cancel, so don't worry about those. Cosine is going to 0, and sine is going to 1. So I get 0 over 1. this tells you that secant and tangent are both going to infinity at about the same speed, right? Because their difference ends up being 0. Okay? If secant had been going to infinity faster than tangent, then you would be getting infinity as your difference. And if tangent had been going to infinity faster, you'd be getting minus infinity. Okay? Right? Or in principle, it could have ended up somewhere in the middle, right? Not 0. Okay, this could happen too. Not as likely. Okay. So I put up a homework sheet with lots of practice at this, mostly the hard ones. You know how it goes. So start working on those. Keep checking the website because I might put some more things up there. Are we still on?
Yeah.
Oh, cool.
We going out?
What's up? Yaman? Yaman in the house!